Math 1314, Section IC1, Spring 2022, Tyler Junior College. Section 4.7, Equations in Quadratic Form. Video 1, what is quadratic form? Now, we've talked about quadratic equations quite a bit. We've talked about what they are. We've talked about how to solve them using factoring, how to solve them using square roots, how to solve them using the quadratic formula. But there are some equations that are quadratic in form in the sense that they're not quadratic, but from the right perspective, they are, and we can take advantage of that. Before we talk about what it means to be quadratic in form, let's quickly remind ourselves what it means to be quadratic in the first place. A quadratic equation is an equation of the form ax squared plus bx plus c equals 0, where a, b, and c are real numbers and a is not equal to 0. It's worth mentioning that you don't have to look exactly like this to be a quadratic equation. You just have to be able to be manipulated into looking like that. Some of them are ready to go, like this one, 2x squared minus 11x plus 12 is equal to 0. That's already in the correct form. But some of them, such as x times x plus 3 is equal to 40, are quadratic equations, but they're just not quite in the right form yet. This one could be turned into the correct form by fixing the reasons that it's not in the correct form. Namely, it's got parentheses on the left and a 40 on the right. We can get rid of the parentheses by distributing to get x squared plus 3x on the left, and we still have 40 on the right. But then we can subtract 40 from both sides to get x squared plus 3x minus 40 on the left and 0 on the right, meaning that at this point, it is in the correct form to be a quadratic equation, which means it was actually a quadratic equation from the beginning. Excuse me. Technically, what makes a quadratic equation is if it is a polynomial of degree 2 equal to 0. When I say degree 2, I mean that the highest power on the x is 2. That's what makes it quadratic. So what do I mean by quadratic in quadratic form? Well, an equation that's quadratic in form looks like this. An equation in quadratic form, and let's highlight that since we're defining it, is any equation of the form au squared plus bu plus c is equal to 0, where a, b, and c are real numbers, a is not equal to 0, and u is any expression containing one or more variables. Now, structurally, this equation that I'm putting in a red box is identical to this equation. The only difference is in this one, I have a single variable x in two places in the equation. And here I have what looks like a variable u, and technically it is, but it's explicitly representing some expression containing one or more variables. So what would an example of a quadratic-like equation look like? Or I'm sorry, an equation in quadratic form. It has many variations on its name. Or for example, if we had something like 2 times open parentheses 3x plus 1 close parentheses squared minus 11 open parentheses 3x plus 1 close parentheses plus 12 is equal to 0. This would be quadratic in form. Now, this technically is also a quadratic equation, but it's also quadratic in form in the sense that it has an expression that occurs twice, once with a square and once without a square. In this case, the expression is 3x plus 1 squared. Notice it shows up once with the square and once without a square. And the expression can actually be more complicated, more convoluted than that. Let me make some room here. There we go. For example, you can have a quadratic in form equation that looks something like this. 2 open parentheses, inside the parentheses is a fraction, and on the top is x squared minus 1, and the bottom is 4, and then that parentheses has a square on it, minus 11 open parentheses inside the parentheses a fraction, on the top x squared minus 1, on the bottom is a 4, and then that doesn't have a square on it, and then plus 12 is equal to 0. Well, this is also quadratic in quadratic form because it has the same expression twice. Once it's squared and once it's to the first power. That's what makes it quadratic in form. It's quadratic not in a single variable, but in an expression. And when you have an equation that's quadratic in form, you can take advantage of that by making what's called a substitution. But we'll talk about that in the next video. Oh, by the way, some equations quadratic in form are a little stealthier. For example, let's say you had 2x to the fourth power minus 11x to the second power plus 12. And you'll notice I'm using the same coefficients over and over. It really doesn't matter. This equation, these two equations, and even the one that's not in a red box yet, but is now, are all the same equation. They have a 2, a negative 11, and a 12. The 2 is in front of something squared. The negative 11 is in front of something to the first power. And then the 12 is a constant. But all 4 of these equations, including this one, are structurally the same. The only difference is what's getting squared. Now, this one's a little trickier because unlike these two that explicitly have a square and a first power, this one does not. This has a fourth power and a second power. But what actually makes something in quadratic form is if there's a repeated expression and one power is twice the other. In this case, the repeated expression is x and one power is twice the other. Now, why does having one power twice the other matter? Well, because if one power is twice the other, then you can write the larger power as the square of the smaller power. X squared squared is x to the fourth. And I'm going to leave this x squared alone. But notice that this is now, in fact, I'm going to not leave that x squared alone. I'm going to put it in parentheses and raise it to the first power. I haven't changed the equation. It's the same equation. I just changed the way it looked. But like all the previous examples of an equation that's in quadratic form, there's something squared and there's something to the first power. The something happens to be a square itself. But what makes it quadratic in form is the same thing is raised to the second power and the same thing is raised to the first power. Sometimes the first power is explicitly written. Sometimes it's implied. There's no first power here, but it's implied. There's no first power here, but it's implied. And everything that has those powers matches exactly. Now in the next video, we'll take a look at how to take advantage of an equation that's quadratic in form or in quadratic form and use that to solve that equation. Math 1314, section IC1, spring 2022, Tyler Junior College, section 4.7, equations in quadratic form. Video 2, making a substitution in an equation that is quadratic in form. In this video, we're going to learn how to capitalize on an equation that's quadratic in form, or in quadratic form, I should say. I'm just going to stop worrying about the semantics. I say quadratic in form. The textbook says in quadratic form. We're saying the same words in a different order, but we're going to show how to take advantage of an equation that's quadratic in form. For example, this is an equation that was illustrated as an example of an equation quadratic in form in the previous video. We have 2 times open parentheses, 3x plus 1 close parentheses, and then squared, minus 11 times open parentheses, 3x plus 1 close parentheses, plus 12 is equal to 0. Notice that this is quadratic in form. It's quadratic in form because it has an expression squared and an expression to the first power. Now, how can we take advantage of that? Well, we can make what's called a substitution. Now, in some upper level math classes, substitutions are very common because what they do is they transform a a complicated problem into a simpler problem. And in this case, what we're going to do is we're going to let the repeated expression be replaced with a single letter. In this case, the repeated expression is 3x plus 1. In one spot, it's squared, and in one spot, it's not. But we're going to say let 3x plus 1 equal any letter we want. We'll use a capital U just to be consistent with the way the equation in quadratic form was defined in the previous video. Now, what does it mean when we say let 3x plus 1 equal u? That means that we can go to any place in the equation, find a 3x plus 1, and replace it with the letter u. Now, I'm going to highlight the 3x plus 1s in yellow. Not the square, just the 3x plus 1s. And this substitution says anywhere we see a 3x plus 1, you can replace it with a capital U or whatever letter you choose to use. For some reason, U is the default. If we do that in the first term, right here, now instead of saying 2 times that yellow rectangle squared, it's going to say 2u squared, because I replaced the yellow rectangle with a u. And if you're wondering what happened to the parentheses, they're no longer required since the thing being squared is a single letter. Let's move to the next term, excuse me. The minus 11 times open parentheses 3x plus 1. Well, again, the 3x plus 1 is getting replaced with the letter u, so we'll have minus 11u. And again, the parentheses aren't necessary there because there's nothing to distribute. So there's only a single term after the minus 11 now. And the rest of the equation stays the same. Plus 12 is equal to 0. And if you'll notice at this point, what we have written in red is now a quadratic equation in terms of u. And now we can solve this. How? Solve this using the technique of your choice. Remember, we have 3 options for when it comes to solving quadratic equations: solve by factoring, solve using square roots, and solve using the quadratic formula. I'm going to solve this one using the quadratic formula, even though I know it will factor. And in fact, in your homework, anytime you run across a quadratic equation at this juncture, it should factor. But let's use the quadratic formula. U equals, I'm just going to call it out and write it down, negative b, so negative of negative 11, plus or minus the square root of b squared, so negative 11 squared, minus 4 times a, which is 2, times c, which is 12. And on the bottom, 2 times a, so 2 times 2. And let's see what that gives us. Going one part at a time, the minus 11 will simply become a positive 11. So we got positive 11 plus or minus the square root of. Now let's focus on the part under the square root. Second, folks. There we go, the part under the square root. Now, if you want to do that in your head, do it in a calculator, that's fine. Do it however you want to do it. I'm going to make my picture disappear for a second, and I'm going to work it above it. Negative 11 squared is 121 minus, there's not a second minus after the subtraction, so it's going to stay negative. It won't become positive. 4 times 2 is 8. 8 times 2 is 96. Excuse me, 4 times 2 is 8. 8 times 12 is 96. 121 minus 96 is 25. Well, that's a great number to have under a square root. Back to the solution, in the bottom of the fraction, 2 times 2 is 4. And now we have u equals 11 plus or minus 5 all over 4, since the square root of 25 is 5. Now we can split this into 2 solutions, one with the plus, one with the minus, finish them. Let me bring my face back in, and we'll go to the next page and finish this. We have u equals 11 plus 5 over 4, and u equals 11 minus 5 over 4. These both simplify pretty quickly. 11 plus 5 is 16. 16 divided by 4 is 4. And on the second solution, 11 minus 5 is 6, which gives us 6 over 4, but we can reduce that by 2 and make it 3 over 2. And now we know what u equals. And you might be thinking, so we're done, except we're not. This equation did not have u's. This equation had x's. We took them out, replaced an expression with the u to make the equation finishable. We finished it. But at this point, our next move, once you solve for u, replace it with what it was representing and continue solving. Whew, horrible job typing this morning. All right, there's another one. Once you solve for u, which we just did, replace it with what it was representing and continue solving. Recall that the u was defined to be what 3x plus 1 is. In other words, we defined our substitution right here when we said let 3x plus 1 equals u. That makes the problem workable. We worked it. Thank you, u. I appreciate you being there. But now I'm going to replace it with 3x plus 1. In this example, we change u back to 3x plus 1. Because that's what it was holding the place of. When we do that, we get 3x plus 1 is equal to 4. And 3x plus 1 is equal to 3/2. And now we finish solving. On the first one, we'll subtract 1 from both sides to get 3x is equal to 3. Divide both sides by 3 to get x equals 1. Pretty simple. On the second one, however, we need to proceed with caution because of the 3/2. If we subtract 1 from both sides, we get 3x equals 1/2. And normally I would divide both sides by 3, but there's another way to get rid of a number that's multiplied, and that's to multiply by its reciprocal. The reciprocal of 3 is 1 over 3. And the advantage to that is on the right side, we have 1/2 times 1/3, as opposed to 1/2 divided by 3. 1/2 times 1/3 is 1/6. And so our solutions are 1 and 1/6. This is really all there is to solving with substitution. It's just a matter of getting acclimated to when to do it and then how to pull it off. The when is when you have a repeated expression, 1 raised to a power, 1 raised to another power, and 1 power is twice the other. The smallest which of it could be is to the second power and to the first power. Then you let u equal whatever the smaller of the 2 powers is, and you transform your equation into a quadratic equation. In this case, the quadratic equation was right here. Come on. Quadratic equation was right here. Then you solve that. And when you solve it, you'll get values for whatever variable you use to make the substitution. I would recommend using u. That's what they do in the homework. The only time you can't use u is when u is already being used in the equation. But after that, you change the u back to what it represented, then continue solving. We're going to take a look at one more example in the next video, but that's really all there is to this. Identify when to do it, make the substitution, solve the quadratic equation, undo the substitution, and then finish solving.